As promised, we're going to start today by looking at some absolute values of these integrations to talk about how they kind of fit together to everything else. We're then going to transition forward into looking at more of the standard using of the other three theorems. So theorem 4.9, 4.10, and 4.11, and then with 4.12. Let's look at the absolute value ones. The main thing that we talked about yesterday was in order to get these to work, you have to figure out the breakpoint where the absolute value causes the change to happen. And then based on that breaking point, split the integral into multiple components that you then evaluate separately using the correct integration. Okay. So let's look at the following integral.
All right.
Yes.
What?
It's good.
It looks like it's
Okay. Here's our first example for the day. The integral from 0 to 4 of the absolute value of x squared minus 4. We're going to attempt to take this integral and solve it manually using the process that we talked about last time, where we take this absolute value, split it at its boundary point, and based on that split, optimize each piece to the correct absolute value function. So let's start with the first component. In order to determine where the split point is, you take what's inside the absolute value, and that equals 0. So what are my split points for this function? In this case, it's more than 1. 2 and negative 2. So I can split this now single integral into multiple integrals using either 2 or negative 2. Which one should I use? Why 2? In our range. Why should I avoid the negative 2? It's not in my range. Yeah. Simple questions that you have to ask though whenever you're looking at a problem. So what I can do now is I do the integral from 0 to 2 divided by x squared minus 4 plus the integral from 2 to 4 divided by x squared minus 4. Once you've now got it split, step 2 is determine if any of these change signs. If they change sign, you need to negate them. If they don't change sign, you need to keep them the way they are. So let's look at this first piece. This one, I recommend using a sample point, much like we did with the first derivative test. So pick a number in the range, plug it in. If it would have been negative, we're going to change this absolute value function into a function with a negative on the outside. If it was going to be positive, we don't make any changes at all. In this case, I'm going to choose the number 1 and number 3 and see if those cause a change. So if I plug in 1, what happens inside the absolute value? So it's negative 3, so it's a negative number. So to fix this, I take the integral from 0 to 2. I take what's inside of this function and negate it. Plus, the other one, the same test. I plug in 3. If I plug in 3, what happens to that function inside? Stays positive, so I make no change at all. I drop the absolute value symbol. And now this is simply power rule problems. Much easier to do than an absolute value question. So from here, I go ahead and solve each piece. You can take the negative over to the outside and solve it separately, or you can distribute the negative and solve it individually. It doesn't really matter that much. Let's do each piece. Negative. X squared. Remember, if you're integrating, it's the opposite of derivative. So instead of subtracting 1 from the power and dividing, you're going to add 1. So x cubed over 3 minus 4x. Evaluate from 4x. So our first piece of integration. So 0 to 2, still negative. X squared becomes x cubed over 3, or becomes 4x. Beautiful so far. Plus, same piece happens over here. But now evaluated from 2 to 4. Now, we'll do each piece separately. I'm going to start left-hand side. Big O negative. Okay. Plug in the 2 first, then plug in the 0. Plug in 2. This becomes 2 cubed over 3 minus 2 times 4. minus 0 cubed over 3 minus 4 times 0. The first piece plus 4 cubed over 3 minus 4 times 4 minus 2 cubed over 3 minus 4 times 2. Yay! That's big, complicated, nasty. That is all calculus should be. Okay, one piece at a time. You can get on, sure. Okay. More than that spacing. Negative up front. 2 cubed would be 8 over 3 minus 2 times 4 would be 8 minus 0 cubed over 3 would be 0. Assuming the negative plus 4 times 0 would be 0. All of that. What we end up with? 8 cubed over 3 would be 24, so yes. So this will become positive 16 over 3 for this first piece. Distribute the negative to all the components. Positive 16 over 3. I'm doing a lot of extra work here. Are there any questions?
Since we already did that, can we put it on?
Oh, heck yes. Please save yourself some headaches. Okay, we already did this work over here. So you know this piece is going to be 16 thirds. Now, when I subtract it, this will become a positive 16 thirds. And then this piece, 4 cubed over 3. 4 cubed would be, what, 64? Yeah. That hurt for a second. 64 over 3 minus 16. This is going to be 48, so there would become 16 over 3. Oh, I got 3 16 over 3s. I guess my answer is 16. So what I suspected. A nice odd number. Huh. These devolve over time into. It turns off again. What the heck is going on? Second. As now. No.
Because what is that negative? Wouldn't it just be 16 3? Or no, that's.
The negative would distribute, and that's why it becomes a positive 6 over 2. Okay. Well, this works. I was going to show you guys a picture of what this function looks like. It's still unique. But the concept stays consistent. If you want to do an absolute value, which is some of your more problems consist of absolute value functions, you have to make sure to break it into multiple pieces, multiple components. So, questions? Should we do another one? This one's okay? Like, what's your guys' opinion?
I just want to see graphics.
Oh. So we have the absolute value of x squared minus 4. Look at that. It's so pretty. It's beautiful. Good times. In this case, in this problem, what we found the area of was. If it's going to be a day, this is going to be a really long, trick day for me. I'll draw everything by hand. It's going to be a day. So, what we found was from 0 to 4. That's rather a strange looking piece of area here. Split between the upper portion of the absolute values on each half. If you don't split it correctly, it's not solvable. can't actually find the solution because you can't split the absolute value of your functions. There is no way to integrate absolute value directly unless you split it apart using beta 4.7. So, again, we took this function, we split it apart at that boundary point. That's the splitting point. Once it was split apart, we then evaluated each piece of that function separately, trying to convert it away from an absolute value into something else. When it was converted back, we could then apply our individual integration rules and be finished. Another? Or move on? There's only a couple easy homework. Not too bad. If you can find the boundary point and answer this question, does it switch? Does it not switch? Go to the street.
Just wanted to find the area that deeper now.
Okay. So, let's continue. Okay. Our next thing. The mean value theorem and its corollary. So, mean value theorem states that for every single range of values in your function, you can determine where there is an average value, what value should rest in the middle. Now, the mean value theorem, which again, as defined last time, this theorem implies there exists a y value in the function which has the average. This is important for a couple of simple reasons. Number one, if this didn't happen, one of two things happens. Either there isn't an average value, which doesn't make sense, because according to the limit idea, we can always turn an area into a rectangle. Or somehow the function skips the average, which also doesn't make sense, but the functions we're talking about are continuous. In other words, if we take a look at a picture, and we take a look at our beautiful picture here, and we're asked to find the area, there must exist some y value, some place on this graph where this happens to be the average height. It can have it in one place, it can have it in multiple places, but it must exist somewhere. It has to be a place in the function on that line that is average. Now, to actually find the x value, so this mean value theorem helps to find the y value. This is really helpful for finding the y value itself. To find the x value, we have a corollary. That corollary just takes that b minus a and divides it over, and it gives the exact same philosophy. It helps to find the actual place itself. So, in each system, in each location, this idea lets us sit there and determine where the value is and what the value is. Now, for your homework problems, that idea takes it a step, because that average is a commonly asked question, and go what that matters. If I'm asking for the average speed, what I can do now is, if I have a graph of the speed, I can use an integral to determine the average. What it does is, the integral finds the overall area, and then I can divide to determine what the actual average itself is. It's a huge advantage in terms of lots of mathematics. Rather than having to do basic summations like we did in the past to find an average, if you think back to find an average in algebra, you use a formula where you take all the pieces, you add them together, and then divide by the total number of pieces. That's how you find an average. But when we're dealing with a function, that's not possible. you have an infinite number of numbers to plug in. So you're taking an infinitely large number, which you're adding together, dividing it by another infinitely large number. That can't work. Instead, we use an integral to do the same for us. So the idea is it takes this function and solves that relatively simplistic algebraic problem and looks at more complex issues and says we can do it with calculus. Here we go. For this function, we're going to determine two things. We're going to determine the mean value of the function, so the average value of the function. We're going to determine where it's at, and we're going to determine what it is. Here we go. Let's take the function f of x
You're in for a long day.
Okay. So we're going to attempt to use this formula in order to determine first the locations of the values, and then secondly the values themselves. It's actually happening to the average, the mean of this function. Here we go. Make sure you have your notes out to indicate what that function looks like. That integral specifically. We have the main integral on the wall now. But the secondary integral, the corollary, is one that should be in our notes from last time. And I'll put them on the board as we get to it. But make sure you have both available. Here we go. Our function in this case, f of x is equal to x cubed minus 2x squared plus 5. We want to find the average value between 1 and 3. I want to do this in two ways. We want to know where the average value is, in one more place, which places those are, and we want to determine what the average value is. So both components, both pieces. So remember, the average is traditionally the sum of all the parts divided by how many parts there are. So now we're thinking of this now with calculus. The sum of all the parts is an integral. How many pieces there are is a value determined by the axes. So here we go. To find the solution, we're going to first integrate from 1 to 3 the following function. X cubed minus 2x squared plus 5 dx. Let's begin there. If we're going to determine the average value, this is step 1. All right. Next. Integrate. How do we integrate this function? X cubed. 1/4 x to the 4th. Minus 2x squared. Beautiful. Plus 5. Plus 5x. Evaluated from 1 to 3. Fantastic. Alright, next phase. We plug these values in. So that means we plug in 1, we plug in 3, we subtract the 1 value from the 3 values. So let's do the 3 first. We do 1/4 times 3 to the 4th power minus 2/3 times 3 cubed plus 5 times 3. There's our first piece. We take the top value and plug it into the new function, what we call capital F of x. Minus 1/4, 1 to the 4th power, minus 2/3, 1 to the 3rd power, plus 5 times 1. People who are really good at simple, basic arithmetic become amazing at calculus when we get to this point, because there's a lot of little math to go through, a lot of little adding, a lot of little subtracting. So let's do each piece one at a time. 1/4, 3 to the 4th. What is 3 to the 4th power? 81. 1/4 of 81 would be 81/4. Minus 2/3 times 3 cubed. What's 3 cubed?
27.
Times 2/3?
18.
18. Plus 5 times 3?
12.
Minus 1/4
It's just times 1, so the number
minus
stays.
2/3
Yes.
plus 5. Okay? Let's distribute. So we have 81/4 minus 18 plus 15 minus 1/4 plus 2/3 minus 5. Okay, looking good so far. I'm going to group terms and simplify. 81/4 minus 1/4.
8 or 20.
20. Negative 18 plus 15 minus 5. Negative 8 plus 2/3. 12 minus 8. Sorry, 20 minus 8 plus 2/3. Would that be like 30/3? Glad you got it. Okay. So this tells me the overall area. Now, according to the mean value theorem, this number is equal to sum f of c times b minus a. Now, there's something you can actually fill in here. We know b, we know a. B is 3, a is 1. Which means that number ends up being 2, which is great. So this 38/3, which represents the area, is equal to 2 times this f value. Now, f, remember, is the original function. This will give us a function that we then have to actually solve by itself. Let's do this. I divide this up by 2, and then with 19/3 equals f of c. Now, first of all, this is the average. 19/3 is the average. But the other piece of this is, where is the average located? There has to be some place on this graph that is at 19/3. There has to be some spot, some boundary point where this function does in fact cross 19/3. That's the last piece of these things. This is usually the hardest piece. This piece before this, doing the actual integration, not so bad. But the last piece, finding the actual value itself, is where we get the most work. So, I'm going to save that number. I'm going to erase everything else. Let's take a look. 19/3 is my average. That number is saved. We got the average. Beautiful. Now the next question is, where is it located? To find where it's located, we're going to determine f of c. That means, where does x cubed minus 2x squared plus 5 equal 19/3? Where is this function actually going to equal that average value? Now, you have all of Algebra 1, Algebra 2, Geometry, College Algebra, Trig available to fixing and finishing this part of the problem. I do not limit how you wish to solve this, but I do demand to get a solution. So, I have found the average. The average is 19/3. Now I got to determine what is the x value, what I call c, where this actually happens. To do that, I have a simple formula. I take that function, I let it equal the value, and now I'm supposed to solve. How do I do that? What do I do from here to solve for that missing variable x? That'd be a good start. Subtract 19/3 over, so I get x cubed minus 2x squared. Subtract 19/3, that would be 15/3. If I subtract 19/3, that'd be minus 4/3 equals 0. What next? Quadratic formula would work with quadratic. That's the quadratic equation, man.
Plug it into the equation. Just use a calculator.
You better believe I'm using a calculator at some point here, right? If it's a quadratic equation works great. Factoring works great. Completing the square works. Like those are all options. If it's quadratic. If it's cubic, I think most of the problems in your homework are either linear or quadratic. I gave you a harder one as an example just so you can see like there's a lot of options available to you. If it's cubic, your options become more limited. So, I tell you find an answer. When does x cubed minus 2x squared minus 4/3 equal 0? What are you going to do?
Use substitution. Okay.
You try it. I'd have to figure out a u. That could be difficult.
Yeah.
You guys are thinking like math students, which I appreciate, but I didn't ask you to solve it in a weird way. I asked you to find the solution. How would you solve this? Like, you this is a homework problem.
I would put it in a graph and look at 19/3 and then find the x from that.
That would probably work. Right? Now you have to do it here, what you're describing. There's a way to do it from here as well. Say again?
Look for the zero.
Look for the zeros, look for the x-intercepts. That'd work. In fact, the only time I'd ever give you an equation this bad would be if it was with a calculator allowed. Okay? Because I want you to have every tool available to you. Like I said, just quadratic formula, use factor, do something else. With a cubic, like there's a lot fewer options. And in case you didn't know, fun fact that I only recently remembered, there is a cubic formula. No. Don't memorize it. Have you seen it? Okay. I need you to work just long enough.
Watch the video, bro. The guy came up with it. I think he was saying that it came with quadratic formula. He came up with it just so he can win competition against other mathematicians that wanted to factor out cubics.
Yes.
Or something along that, I can't remember the exact.
There are certain cubics that have a faster way to do it, but there is a general quadratic equation, or a general cubic equation. It is big and nasty. That's why I recommend not learning it. Like, the quadratic equation, it's not exactly small, but it's totally doable to memorize it without too much trouble. This thing, like, just writing it down would take up more than a line of text, like, by itself.
Yep. Calculator.
So yeah, you better believe I'm going to do a calculator instead. So there is a cubic formula. Let's see what I can show you. Don't tell me yet. There it is. Yeah. You and the thing is, like, if you notice, there's no difference between top and bottom other than one symbol change. So it's not as hard as you think it's going to be. It's just it's a lot.
Wait, is that like the top and bottom, the entire thing?
Yeah, it's all one equation. The top plus this minus that. It's nasty, it's big.
Calculator.
Did you find the solution with the calculator?
I got 2.26 and negative
2.26 and negative 0.13. You'll notice that 2.16 is in this range.
Yes.
That's the one that's the solution here. So my x value is 2.16, you said?
Or 2.26.
2.26.
Yeah.
There are my two solutions. I don't want to say it this way, but you have a lot of tools available to you. Don't get stuck in the mindset of my math teacher wants me to do it a certain way. Miss Martin wanted me to do it a certain way. Miss Park wanted to do it a certain way. Mr. Ford wanted to do it. You are tasked with solving. You've proven you can do the calculus side of it. Do what you feel is necessary to solve the other part. Okay? Take that initiative of, I can just plug it into a graph as long as I got my graphic calculator with me. Boom, done. Well, you better make sure when you take your test, to this portion, you have a graphic calculator. Alright. So we had one where it's nastier than what I expect. So let's do one about the level I want you guys to be able to do, which is a quadratic version. Okay. Let's do it. It hasn't failed yet. I'm trying to jinx it. Please fail? No? Okay. To showcase ways you can use your graphic calculator for this, we have x to the third minus 2x squared plus 5. Different function.
Go to 19.
Go to 19 thirds. That'd be one way to do it. You can see from 1 to 3, there's one spot where that happens.
The rest are
You have to imagine. Alternatively, once you've already set it equal to 0, we have what, negative 4 thirds there? Minus 4 over 3. You can look for the intercept instead. Who does that go? You have so many tools available. Please don't get locked in the minds. Everybody does. We get so used to how everybody wants it done in other classes in calculus. I hate to say it, but we look at it and go, that's somebody else's job. Okay, you've proven you got the calc side of it. Take your easy steps to get to the other solution. All right, let's do another one. We'll finish the class in this one. Okay, we're going to determine the average value, both the y value and the x value of the following equation. 3x squared minus 5x plus 4 evaluated from 2 to 5. I'm going to determine the average value and where it's located. Here we go. If I'm asked to find the average value using calculus, how do I do it? Integrate. From 2 to 5 of my function, 3x squared minus 5x plus 4 dx. When I integrate, what do I get? Beautiful. X cubed minus 5 halves x squared plus 4x from 2 to 5. Okay, now what?
Plug in 5 and 2 in this graph.
Plug in 5 and 2, so 5 cubed minus 5 halves 5 squared plus 4 times 5 minus, plugging in 2 cubed minus 5 halves 2 squared plus 4 times 2. Alright, this will determine the average. Okay, 5 cubed minus 5 halves times 5 squared. Cheating helps here. What's 5 squared?
1 over 2.
1 over 2.
Plus 20.
Plus 20.
The hardest part.
Minus 2 cubed.
Oh, it just says I just get the bonus solutions.
Minus 5 halves times 2 squared. 10. Plus 8. Okay. So 1 piece at a time. 125 minus 1 over 2 would be 125 over 2 plus 20, which would be 40 over 2. That'd be 165 over 2 minus 8 and 8 makes 16 minus 10. That'd be 6. 165 over 2 minus 6. This becomes 12 over 2. This becomes 153 over 2. Okay. So my average value is around 76.5. That's pretty high value. So my average, 153 over 2. So next, wait, hold on, wait a second. According to the mean value theorem, this is equal to capital C times E minus A. Now, this means that to find the average, we have to plug in P minus A and divide to get f of c by itself. That's the average. This is not the average. Remember, this is not finding the average value. This is the area we just found. Let's find the average. Find the average, we take 5 and 3, plug it in. We get 3. Divide it over. So again, the area is 153 over 2. We get 153 over 2 equals f of c times 3. Divide 3 over, what do we get?
51 over 2.
51 over 2. Or around 25. Again, small difference there. Even I almost moved on. Like, it's easy to forget that does not tell you the average value. All we found was the area. To find the average value, we have to fix the other half of the formula, plugging in the b and the a. Okay, so average value is now found. And when we graph this thing, you'll see that that 153 over 2 is clearly not the average. It'll be way outside the rest of it. Okay, now let's find where that's located. And the average. Next piece. To find the actual value itself, we take 3x squared minus 5x plus 4 and plug it in. 51 over 2. At this point, what are my options? I cannot do the quadratic formula right now until I have subtracted over, and then I can do the quadratic formula. What else can I do? We complete the square? Yeah, that's still about it. We graph it? Yeah, that's good. I can try to factor this? Yeah, all these are possible. Okay? You've got to find a way to find a solution. Me personally, I'm going to use the quadratic formula. So I'm going to start by subtracting over and then plugging everything in. I'm probably not going to finish it because we're running out of time, but I will at least have the answer and be able to circle it. Here we go. Subtract 51 over 2 over. So if I do that, I end up with 3x squared minus 5x. Subtracting 51 over 2, that becomes 8 over 2. Subtracting from that becomes negative 43 over 2 equals 0. Plug in the quadratic formula. Negative b plus or minus square root of b squared minus 4a c all over 2a. Now, it's possible both of these are in this range. It's possible only one of these is in this range. But there has to be at least one. So remember, there has to be a place where there is a solution that's according to mean value theorem. So I'm going to simplify a little and see if I can make some guesses here. So I have 5 plus minus, okay. 4 times 3 times negative 43 over 2. So I'm going to cancel the 2 with the 4, leaving there 2 there. 2 times 3 is 6. Times 43 would be 258. So I end up with the square root of 25 plus 258 over 6. That was big. Okay. 25 plus 258 is going to be 5 plus or minus the square root of 283 over 6. Now, the square root of 283 is bigger than 5. The square root of 25 is 5, so 283 is going to be much bigger. Which means that if I subtract, I'm going to get a negative number. Does that make sense? And a negative number cannot be in this region. So that tells you my solution must be 5 plus square root of 283 over 6. Now, that's not good enough for me. I want to know what that is. 5 plus square root 283. All divided by 6. 3.637. That's in the range. Let's see if that's right. So now I'm going to use the graphing version instead, try to solve this problem differently. So I'm going to take my original function, 3x squared minus 5x plus 4 I'm going to take the function y equals 51/2. Where is it? Got it. Little picture one. Yeah. Okay. Mean value theorem and its corollary. We'll do another example of this tomorrow. And we'll move on to the next theorem. The second fundamental theorem of calculus. I'll see you guys then.